We're going to be kicking this off with Dr. Clement Vidal. He's a philosopher with a background in logic and cognitive sciences, currently a visiting researcher at the UC Berkeley SETI Research Center. He's the co-founder of the Evo Devo Universe community and author of The Beginning and the End, The Meaning of Life in a Cosmological Perspective. He's eager to tackle big questions, bringing together areas of knowledge such as astrobiology, cosmology, physics, complexity science, or evolutionary theory. You can find more info at clemvidal.com. The title of his talk is The Spider Stellar Engine, a Fully-Steerable Extraterrestrial Design. Clement.
So for the arachnophobic people still in the room, I reassure you this is the only spider image that I will show. So I'm not going to tell you how I got interested in space by just looking at the night sky, but rather what I want to tell you is that nowadays I have a totally different view when I look at the night sky. Namely that stars are the obvious source of energy for the long term. And so civilizations, these are bounties, energy bounties for civilizations in the future, or maybe already in the present, that are using very effectively stars. And so this leads to the idea of type 2 civilization on Kardashev scale, which is simply an energetic scale. And as we saw this morning, we are presently at 0.75, so almost type 1 civilization. And the point here is that this phase transition between a civilization that grows to a civilization that is able to exploit the output of its star is extremely short. It's extremely short. So we are likely to find either primitive biospheres or type 2 civilizations. So that's the argument here. What are the examples of type 2 civilizations? You probably know the Dyson sphere idea or Dyson swarm, so to place solar collectors around a star to capture its energy to do whatever they want. I propose an alternative to Dyson sphere that I call the Stellivore hypothesis. And it's a reinterpretation of some accreting binary stars as living in the following sense. So you have the companion star, that is the energy source. There is an irregular flow, which is a very important point, is that some of these systems have a flow of matter accreting that starts and stops. And that's a fundamental property of living things. They are able to budget their energy. If you eat all the time, you die. If you don't eat at all, you die. You need the right throughput. And they also eject jets or novas in the case of white dwarfs, which I propose to interpret as entropy, waste, that also all living things have to do to eject waste. And so the big question is this life, and how can we test that? So I would like to ask you to put yourself in the shoe of a stellivore and imagine that you eat a star, and through the millions of years, then you have almost finished to eat your star. What would you do? Find another star, of course. So that's what I did with some colleagues, is to look if some of these systems with a very low mass companion star are actually goal-directed. And this is one example of the original Black Widow pulsar. So in blue, you see the binary star. And we queried the surrounding stars with Gaia, and we tried to see which ones would be the closest. And for example, here, the nearby star is here, and the closest approach is here, that will be attained in 420 years. It may seem a lot from a human time scale, but it's extremely short for this kind of encounters. So tell your grandchildren to watch this. And here you see the same in X-ray, thanks to ESA Sky. And this is a composite image where you see in X-ray the red part, and the bow shock here is in optical. And now the moment that you await is, how do they do that? How would they go to this other star? What is the mechanism? And I'm glad to reveal to you the Spider-Stellar engine. So what is it? It's a payload of 1.4 to 2.1 solar masses, so it's rather heavy. The propellant mass is, I told you, a very low mass companion star. So there are two kinds of spider pulsars. One are called redbacks. These are two names of different kinds of spiders. They were named after this because they actually consume the companion star. And if the companion star is almost evaporated and weighs 0.01 solar masses, it's called a black widow. And their velocity vary from 11 to 231 kilometers per second. So again, I would like to emphasize here that the phenomenology is actually very different from other accreting binary. The logic is really reversed. So normally an accreting binary just sucks in energy from its star. But here, it's actually evaporating the star. And so this triggers the question, could this create some thrust? And since we are speaking about a binary system, of course, the dynamics is peculiar. It's unlike any spacecraft we know, because a binary is in orbit. So you have the pulsar here and the companion star. And to create thrust, you would need to time actually the pulsation or the evaporation just at the right moment. Come back here. So for example, if it wants to continue going forward, it needs to evaporate the companion just at this moment to propel it forward. And yes, it's a bit uncertain, but there are some indications that there are pulsations that are at the orbital period phase, once per period. So here it's a 2-period diagram in gamma rays of this pulsar. But yeah, it could be also some observation effect that we see an eclipse at this moment. And so I'm not 100% sure that it's really a pulse at the right position, but it needs to be further investigated. But so since we have quite some parameters for these systems, we can estimate the escape velocity, because thrust, by definition, needs to have mass that is expelled out of the gravitational band of the system. So I just did a simple Newtonian calculation of the escape velocity. We have the total mass of 2.14 solar masses, and I just assimilated the whole system as as a point mass system with a separation of 10 to the 9 meters, which is the typical separation of this kind of binaries. And so it leads to an escape velocity of 753 kilometers per second. And now we have enough to try to compute the rocket equation, the first version of it. So we have the exhaust velocity that we can approximate with a minimal escape velocity. The initial mass would be the redback that has still a big companion star. And the final mass would be the black widow configuration that has almost finished to evaporate its companion. And we find a delta V of 141 kilometers per second, which means a specific impulse of 76,000, which is big. So thrust is not everything. You also need to be able to accelerate and decelerate properly. I wish somebody could bring me an umbrella to show something? So here you see, probably slightly in red, what's called the intra-binary shock that has been modeled to explain the very peculiar phenomenology of this system. And in this case, it wraps around the millisecond pulsar. So it's as if it's like that. But in black widows, the intra-binary shock is actually the other way around, like this. And that's exactly what you would want to do to have a kind of a strong braking capability. And so, yes, also I should add that this shape depends on whether the millisecond pulsar magnetic field overpowers or not the magnetic field of the companion star. So here it's lower, and here the magnetic field is stronger than the magnetic field of the companion star, so that's why it can wrap around it. So just so you remember, red backs like this, and black widows like that. And I'm not making this up completely. There is actually a code to model this intra-binary shocks that is called the umbrella code. And now you might have a feeling of déjà vu. Yes, you have already seen this animation. How do you steer the system? Yes, that could be a one way indeed. I haven't thought systematically about it, but another simple way is that might be complementary, is simply to pulse the evaporation at different times. So here, for example, if the pulsar would evaporate at this time, it would tend to push it in that direction. So it's actually a very natural way to steer in the orbital plane. I propose to call it 360 thrust vector control. Okay, but now we've seen how they could steer it in the orbital plane, but you still don't have full control. To have full control, you need to be able to steer in the last remaining direction, which is out of the orbital plane. And interestingly, in some systems, the light curve is complicated, and a direct heating model of the companion star doesn't work. And we need to assume that there is an asymmetric heating of the companion star. And for example, this is a hotspot model. So you see that it's slightly up of the center of the companion star. But yeah, so then it's probably a delicate maneuver if you would push the companion star towards its bottom. It would tend probably to lift it up, but then you need to stabilize it. You need to stabilize the new orbit. And there is a relatively new paper that has found a puzzling 2-hour X-ray periodicity in the 1.5-hour orbital period Black Widow, PSR J1311. And what I did is I wanted to visualize what this means. So I made a little diagram of the first X-ray pulse. So this is the millisecond pulsar. The companion orbit is there, and the first X-ray pulse is at point A. Then you wait 2 hours. You have another X-ray pulse at point B. 2 more hours, another X-ray pulse at point C. And so what's interesting here is that you have this actually very symmetrical tripartition of the orbit. And if you think about it, how can you hold a plate like this? If you do it with 2 fingers, it's impossible, or it's very unstable. You need 3 fingers at least. Yeah. So to conclude, this idea of using a star for very long interstellar travel was already envisioned by Stapleton, who wrote that for longer voyages lasting for many thousands of years, the only method was to form a small artificial sun and project it into space as a blazing satellite of the living world. So to conclude, I've proposed a reinterpretation of spider pulsars, and I showed that the spider stellar engine appears to be fully steerable with thrust, acceleration, deceleration mechanisms, and that it's possible to steer in the orbital plane with the 360-degree thrust vector control, and steering out of the orbital plane thanks to an asymmetric heating of the companion. Thank you for your attention, and if you want to reverse engineer an ETA candidate rocket, let me know.
All right. Thank you very much for that. We've actually got plenty of time for questions and still to be able to keep ourselves on time. So I see we've got the runners, so we'll start over here.
Yeah, hi. A lot of interesting ideas, I guess, come out of misunderstanding a slide. So I saw one that was, it looked like a map of other star systems. And I wonder, actually, from looking at that, if you've looked for evidence of another culture eating stars, like they would leave remnants behind them as they move to the new feeding ground. You think you could see that, which might be interesting.
Well, I mean, in this theory, they would use the end of their fuel, the end of their energy of their companion star to go to the next star, and so what remains, even the black widows, have a mass of 0.01 solar mass, which is amazing that we can actually observe them. And the reason we can observe them is that it's because the pulsar actually irradiates them very powerfully. And that's what makes them bright. But if the pulsar wasn't here, I guess we can detect any star that is, any isolated star at least, that is 0.01 solar masses or less. And I'm not sure which map you're talking about because yeah. Yes, maybe I went a bit quickly here. So what we did is, so what is your question here?
Stars on the trail. The evidence actually.
Well, you have this X-ray trail. But yeah. This X-ray trail that is aligned with the star here, that is in orange, and that is here also. That, well, you don't see in X-ray, but you can see in the optical. That Gaia can see in the optical.
Clement, thank you. It's a great paper. And you're one of the few people who, like me, has looked into what philosophers call panpsychism, what science fiction writers call stellar volition, and what astronomers and biologists call self-organization at various levels. The question I have is, who do you think is in charge? Is it the star or is it the people on the planet? You know, this is the star carrying the people on the entities on the planet, or are the entities on the planet directing the star?
So I don't need the hypothesis of planets to paraphrase.
Okay.
I mean, I know it puts off a lot of people, but the way I see life is in the most general term, in a systemic way that needs to be able to perform some function, to be intelligent. And in the same way as you can have computer or hardware with very different kinds of computers, and we have seen already 6 major hardware changes of computers, and in the future we'll have quantum computers that will look nothing like our computers now. I believe that in the future life can transition to other substrates. And recently we've had a kind of demonstration of this with artificial intelligence that can display some kind of intelligence. We can argue how far it's intelligent, but it has some kind of intelligence, and yet it's not based on carbon. It's based on it runs on computer hardware.
I have one question, one comment. The first slide you showed, is that a compact object that's, so that's either a neutron star or a black hole. So you're talking about moving stellar masses. And is that right? I mean,
yes, that's right. That's the concept of stellar engines. There are a few papers, a few theoretical papers. Actually, so here is the almost comprehensive bibliography on the subject.
have you? Oh, you do have Shakadal there, so yeah, you know about his proposal. Yeah.
Yes, I mean, I'm not a physicist, but from what I've heard, that it could be hard to maintain the mirror on the other side.
Yeah. Well, that's type 2 civilization.
Yes, so yes, it's an engineering problem in the end. Yes.
Your situation, though, I mean, the civilization is going to be in a very unfriendly environment before it reaches the time where there's an accretion disk around the compact object. Yeah, they may just take off already.
Yes. Yes. Well, yeah, we need to discuss more. But yes, I mean, there are many leaps of why a civilization would become like this, and I've published about this. I'll be happy to share my papers about this issue.
So, if I'm understanding this correctly, the very dense object is blasting the other star with X-rays. Are you saying that they're controlling this? These other civilizations are controlling a black hole or neutron star to pulse when they want, or do they have an amazing X-ray laser? And should we be looking for evidence of that instead?
No, I'm saying that they are living on the surface of the white dwarf neutron star, or in this case, neutron stars. It was neutron stars. So yes, in the same way that to have life, you need chemical reactions. I suppose that advanced life could organize its reactions and its complexity with chemical reactions with nuclear reactions or subnuclear reactions in the case of neutron stars, which of course remains a big question mark, but
we have time for just one more. Michelle?
I was wondering, if do you actually need a civilization, or can you see the neutron star as an entity, or like a cellular organism that would develop what seems like basically fairly simple mechanism? There's food, and I can point this jet to the star, and interesting things happen. I get closer to the food. So do we need a civilization for this, or do you think it could be a sun-sized organism which is doing its thing out there in space?
Yeah, I can't rule out this possibility, but it could be even, yes, a rather simple organism, but that is just on this monumental scale, and that happens to feed on stars. I can't rule it out. I intuitively don't like it much because it's not how cosmic evolution has worked. Evolutionary systems are able to harness more and more powerful energy gradients through time. So I suppose that doing this kind of stuff would be actually super hard.
All right. Thank you very much, Clement. Appreciate that.